Okay. Alright. This is the lecture note under week 6. Alright. So this lecture note has been given to you yesterday, so that you can download and print out during the lecture. So the reason I asked you to print this lecture note because I want you to write it down. Because when you use your motor skill, you write it down, you can remember easily. Alright. So this is lecture note fluid mechanic 1. So today we're going to study or understand the description of fluid motion. Secondly, classification of fluid flow. And finally, the Bernoulli equation. Okay, my name is Muhammad Nur Hidayat. Okay, I will be your instructor for this session. Okay. What do you understand about the fluid flow? Previous class we learned about the fluid. What do you understand about the fluid? Anyone? What is fluid? What do you know about fluid? The fluid is any kind of matter that can deform by the external force. Alright, can be continuously deformed due to the external force. Okay, so description of fluid flow. That means we need to study the parameter involved of the fluid flow. For example, the velocity, the pressure, how it moves, the direction of fluid flow. Okay, so allow us to get a more detailed analysis of the flow. Okay. Alright, so by understanding the description of fluid flow, we will get a lots of detailed analysis of fluid flow. For example, okay, example number 1. Alright, can you mute your yourself? Okay. So example that we can get the detail, for example, we need to know the flow velocity, varies across pipe section. Alright, for example, we have the pipe section here. Okay, this is the pipe section. So across the pipe section, in the cross-sectional area, we have the flow. The flow will be like this. Okay, this is we call the non-uniform flow. Okay, so we need to study the velocity different at this point, this point, this point, this point. That is why we need to understand the description of fluid flow. Okay, the second example is that how does the pressure vary along the surface of an airplane wing. Okay, this is more on the aerofoil. Right, so for example, we have the aerofoil shape of the wing. Okay, this is the wing of the airplane. So the pressure will varies from here. Okay, we have a different kind of pressure distribution. Okay, the pressure at the bottom will be different at the top due to the due to the Bernoulli principle. Later on, we're going to discuss. Okay, so pressure at 1 is different with the pressure at 2. Okay, definitely pressure at 2 is higher than pressure at 1 due to the Bernoulli principle. So that is why we need to understand the concepts of descriptions of fluid flow in order to understand the details of the velocity profile, the pressure distribution across the airplane wing. Okay, so secondly, we need to understand the relationship that apply to a point. All right. For example, this point to this point, we need to know the relationship. That is why we introduce you the governing equation that we going to explore, which is the differential equation, or sometimes we call a differential analysis. Okay. In the fluid description flow, okay, we have two types of description. Right, the first one is a Lagrangian description, and second one a Eulerian description. Normally only two you need to memorize. Okay, the first one, okay, when we talk about description of fluid flow, we have two. Lagrangian description. What is a Lagrangian description? Okay, Lagrangian description is a fluid, okay, fluid particle, okay, fluid particle selected and the position positions, velocity would be the functions of time. All right, so that means this is dependence on the time. Lagrangian description rely entirely on the time. All right, so that means the fluid particle that is selected and the positions, the velocity will be the functions of time. All right. For example, I will give you one example. We have the root. Okay, we have the root. Okay, and then we have the police. Okay, and then we have a car. Okay, we have a car moving. Okay, so this police is actually monitor car one by one. Okay, this is car A, this is car B. So basically we can say that the police monitor, okay, monitor car individually. Okay, so it will monitor one going through. So that means it will monitor only this car only. Okay, so how about the Eulerian description? Okay, so basically the Eulerian description thinks of the control volume. Okay, we need to think of control volume or consider looking through, right, looking through a window and watching flicks. Okay, so here the individual, all right, particles are not monitored. Okay, so that means we are not monitor individually of the particle. Okay, what actually the Eulerian measures? Okay, this is why the third point is actually, okay, the property, the free particle, okay, that is measured as a function of time and space. Okay, so this is the keyword. The Eulerian focus on the time and space. What do you know of space? Everyone, what do you understand of space? Anyone would like to try?
Maybe the displacement. It goes from point A to point B.
Yes. Basically, it is related to the location, displacement, or the coordinate. Okay, X, Y, and Z. Okay, we have the space here, the 3D space in our world. So we have the coordinate X-axis, Y, and Z-axis. Okay, so how can we relate to the policeman here? Sorry, yeah. Okay, how can we relate to the policeman? Okay, for example, we have the road. Okay, we have the road here, and then you have the car here. Okay, we have different kinds of car. Maybe this is car A, this is B, and this is C. Okay, this is the policeman. So what's the policeman do? Remember, it is the particle are not monitored. Alright, individual particle are not monitored. So what's the policeman do? It is actually monitor only this portion. Okay. It is only monitor the location only. So how many of car pass through this intersection? So basically, this is the analogies to what we do to compare from the Lagrangian to the Eulerian. Alright, so that means you can see Lagrangian follow the individual path of the car. Alright, for example, the car will move from here, will move through all this area to this location. This policeman will monitor until this one. Alright, will monitor individual of the car. However, for the Eulerian description, the police is not monitor the individual car or individual fluid particle, but monitor only this section, how many car across this section, what's the velocity of this car, right? The pressure or any kind of property the car pass through this location. Okay, so far you guys understand the concepts of Lagrangian and Eulerian?
Yes, doctor.
Okay, good. Okay. So, normally, this is the description. However, remember we need to relate to the sums of the governing equation in order to know the details of this velocity 1, pressure 1 or pressure 2. That is why we're going to relate to the Newton's law for the Lagrangian viewpoint. Okay. So we're going to apply the Newton law, which is, okay, for example, Q can be any kinds of property, whatever property, you know, like velocity, pressure, temperature. Okay, so we can use the law dq. Remember, Q is any kind of property over a dt. Okay, don't confuse, yeah. D is a total differential. All right, this actually, the capital D refer to the whole of the property. Okay, it is actually equal to the dq over a dt. Okay, when I talk about total D, or sorry, the capital D, that means it is the whole. For example, we monitor in terms of X, Y, Z, axis, the whole of the things we monitor. All right, and then it is actually equal, the same with the dq over dt. Okay, this is doesn't matter, it is the same. All right, but the difference is the notation. Okay, and then, as I mentioned before, this is the whole. That means we monitor in terms of X, Y, and Z. So for this case, we need to separate in terms of X, Y, and Z component. Remember that when we talk about the Eulerian description, we focus on the time and the space. Right? So basically, this is the Lagrangian we convert into the Eulerian. You can see? Right? That is why we need to use the Newton law. Alright, so we need to use the partial derivative of Q over partial derivative of T. Alright, why we use the partial? Because when we talk about partial, that means we focus on individual property, not the whole. Okay, multiply with the, okay, dt over dt. Alright, remember that the Eulerian is the function of time and space, which is X, Y, and Z. We use the Newton law to convert from the Lagrangian to the Eulerian. This is how we convert. Alright, so this is in terms of time. And the next one is in terms of the space. Alright, the partial derivative of Q over partial derivative of T. Okay, but for this case, it is quite different. Why I say different? Because we're going to use the chain rule, right? The partial derivative of Q over partial derivative, sorry. Okay, this is dt. Okay, this is partial derivative of X, and this is the dx. Alright, when you try to cancel, can you see? Alright, this is X, we can cancel out. We can get partial derivative of Q over T. Okay, this is in terms of space in X direction. So we need to continue in the Y direction. Okay, this is Y, this is dy over dt. Right, this is space in terms of Y, and finally we have the space in terms of Z. Okay, multiply with dz over dt. This is the space in terms of Z. Can you see we complete together time and space? Okay, and I would like to highlight here that the Q can be any fluid property, such as velocity, pressure, or temperature. Okay, the Q here. So from here, Okay, you can see dt over dt is equal to 1. So we can say, we can simplify, okay, partial derivative of q over partial derivative of time, okay, plus partial derivative of q over partial derivative of x. Right, for this case, you can see dx over dt. Okay, this is your axis. This is x, this is z, and this is y. When you have the change of motion in terms of x divided with time, you will get the velocity in x direction. So the velocity in x direction we call as the u, right? This is the notation. Okay. For the y, the velocity in the y we call as the v. Velocity in the z notation we call as the w. That is the vector for the different velocity. Okay, when we talk about u, that means it is dx over dt. So we can simplify here, dx over dt is u plus partial derivative of q over partial derivative of y multiply with v plus partial derivative of q over partial derivative of x multiply with w. So this is the equation that we use to convert from the Lagrangian to the Eulerian points of view. Sometimes all these terms we call as the material derivative. Okay. Okay. Alright. So we will describe the fluid motion in terms of velocity and acceleration. So now you look at here. Q we call any kinds of fluid property like velocity, acceleration. Now let's try to derive clearly in the points of velocity field. Okay. So field representation is equal to the representation of fluid parameter as a function of spatial coordinate. Alright, that means we use the partial derivative to represent the coordinate of x, y, and z. Alright, it may be different at different time and need to find parameter as a function of coordinate and time. Okay, this is what we call as the Lagrangian description. And we need to find the parameter as a function of coordinate, which is space and time. This is Eulerian. Okay. So, let's start by establishing the coordinate. Okay, this is the coordinate. Alright. Normally we use Cartesian coordinate, which is this is x, this is y, and this is z. Okay, and when we talk about the unit vector, okay, when we talk about unit vector, definitely the unit vector in terms of x direction we call as the I. Alright, the unit vector in terms of the y we call as the j, like this. And then in terms of in terms of j, it is actually k. Alright, I hope you understand the basic principle of the calculus. Have you taken calculus before as your subject? Anyone? Anyone taken the calculus? You guys, are you there?
Doctor, yes.
Not yet.
Not yet. Oh,
No, doctor, we took calculus. We had math 1 and differential in second sem, first and second. Fluids is third sem. So we took calculus.
Okay. So basically, you guys understand, yeah? This is actually very basic principle. The I is the unit vector in terms of x direction, j and k. Okay, that is simple. Okay, now we establish in terms of v. Okay, this is in terms of velocity. Velocity, remember, it is a vector quantity that has the magnitude and the direction. Okay, so we have the u, okay, in terms of x, y, and z direction, as well as in terms of time. Remember that this is the Eulerian description. We have the space and time. This is velocity, and this is velocity in terms of magnitude, and this is the direction. Alright, plus v in terms of x, this is coordinate of the velocity, x, y, and z, as well as time. Okay, and then this is I, this is j. And finally, this is w, and the coordinate of x, y, and z. This is k. Okay, this is how we express the velocity vector in terms of I, j, and k. Okay, this is we call as the velocity vector in the Eulerian description, because we have the space and we have the time. Combination of space and time is what we call a Eulerian description. Okay, this is in terms of velocity vector. If you want to find the coordinate, if you want to find the magnitude only, it's a very simple. It is the square root of this part, u squared plus v squared plus w squared. That's it. Okay, so far you guys clear about the velocity field in the Eulerian description?
Yes, doctor.
Okay, for the velocity is quite easy, only short version. How about the acceleration? Okay, for the acceleration part, okay, I need you to focus more. Okay, so acceleration. What's the formula of acceleration? Acceleration is a vector. You put here vector is equal to dv over dt. This is the standard, right? Since v, okay, since v is a function of space and time, all right, remember the space, we have x, y, and z. Thus, we must use the chain rule because we need to make the correlation between the space and the acceleration here. Okay, so we must use the chain rule. Okay, so A equal to dv over dt equal to partial derivative, remember the same thing, dv over partial derivative of time, this is multiplied with dt over dt. Remember, this is what we want to see in terms of time, and plus, okay, partial derivative of v in terms of partial derivative of x, this is dx over dt, plus partial derivative of v in terms of partial derivative of y. Remember, this is what we show in terms of coordinate. Okay, this is dy over dt. And finally, partial derivative of v over partial derivative of z. Okay, this is dz over dt. Okay, remember that previously we know that this term, okay, is u, where u equal to Sorry, not this term. This term. Okay, this is u, where u equal to dx over dt. V is equal to this term, okay, dy over dt, and w is a dz over dt. So we need to replace this term. Okay. So now we try to replace a equal to dv over dt. Okay, equal to d. This one is cancelled. Okay, this is the same thing, dv over dt, okay, plus this term. Okay, u we try to shift forward, u partial derivative of v over the partial derivative of x. This is v partial derivative of v over partial derivative of y plus w partial derivative of v over partial derivative of z. Okay, so so for this case, okay, this is the term. Alright, remember that the acceleration is the vector quantity that have the magnitude and direction. So we can actually express this is the whole of acceleration. So we can actually express the acceleration in terms of x direction only. Okay, how to do that? That means we change, okay, this term, the v here, this is the total v with u. Remember u in terms of x. Okay, so from here we can change this term only with u. So partial derivative of u over partial derivative of t plus, this is the same, u partial derivative of u, only change this one because we express in terms of x. Okay, plus v partial derivative of u over partial derivative of y plus w partial derivative of u over partial derivative of z. Okay, so in other words, we can convert all these terms to the simplification form. Okay, for this part, partial derivative of u over partial derivative of t plus, I believe if you learn the calculus, you will know that this term partial over partial derivative of x, y, and z, we can convert into solve this term. Okay, velocity multiply with the dot product. This is gradient form. Okay, multiply with u. Okay, where basically this term is actually equal to, okay, d dx, this is in terms of I, plus d dy in terms of j, plus partial derivative of z in terms of k. Okay, this is actually the simplification form in terms of vector. If you learn the calculus subject, you can simplify all these terms in terms of this term. Okay, you can see here when we multiply with u, alright, when we multiply with this term, we can get the same thing here. Okay, this is u, and this is u. Okay, alright, this is I, J, K, we refer to u, v, w. But remember, we multiply with the velocity, so it becomes the velocity in I direction, velocity in j direction, velocity in k direction will reflect to u, v, and w. Okay, so far you guys understand until this part? Everyone?
Yes, Doc.
Okay. So this is what we express in terms of x. So of course, we need to express in terms of y and z. So let me make it quick. Okay, this is in terms of y equal to, this is in terms of v. Okay, remember that the velocity in the y direction we replace with the v here. Okay, over t plus u, v and w fixed u delta v over the change of x v, okay, w, okay. So we can, the same thing happen, nothing change, right? The change only the v. Okay, dot product with the gradient form multiply with the v. Okay, and then this is in terms of the z, which is, this is w over t plus, this is the same. Okay, this is z. Sorry. Okay, so we can put this way. All right, now complete. Okay, so based on this one, okay, we can say that we can do the simplification, the whole of this term. Can you see this is in terms of x, y, and z? We can do the summation of acceleration, okay, in the vector form equal to d, this is total, okay, derivative v over dt equal to d v over dt plus, this is u dv over x, okay, this is the total one. Okay, this is combination, yeah. This is v over dy plus w v over dz. Okay, can you see this one? Okay, this part. Actually, we take out this one into this one, and we can simplify this term into of dv over dt okay, plus this is velocity dot product with the gradient form multiply with v. Okay, where normally we call this as the local acceleration. Okay, normally we use, right, the velocity over time. However, for this part, we call as a convective acceleration. If acceleration. Okay. This is what we do the derivations of velocity and acceleration field. Okay. So let's try one example. Okay. So we have the 2D velocity field is given by, you can see when we talk about 2D, we only have I and J direction. We don't have any third direction, which is K direction. At the location of x and y equal to 1 to 2, compute the acceleration in terms of a, x, and ay. Okay. So what's the, okay, when we look at here the question, this is the velocity vector. Okay, why velocity vector? Because we have this is the magnitude and this is the direction. This is magnitude and this is direction. Normally the velocity vector, okay, we can compare with the v equal to ui plus vj plus wk. So now, what the u represent and what the v represent? Anyone would like to try?
The U represent the X.
X only?
Oh, the
Okay,
X minus
is,
y squared plus X.
this is u and this is
V.
v, yes. And this is v. Because why this is v? Because this is the velocity in the y direction. We need to take, okay, negative 2xy, negative 1. Okay, this one we try to solve and open the bracket. Okay, so how to get the acceleration in the x direction? Remember, we need to use the formula. What the formula that we have derived before? Can you see here? This is the formula. Okay, so write it down, the formula. So the formula is, okay, partial derivative of u over partial derivative of time plus u du over dx plus v du, du over dy plus w du over dz. Remember that this is only 2D. So the w direction, can you see w is 0. So we can cancel out this one, become 0. So can you see here? Do we have any unsteady state? Can you see here? Our u and v component, do we have in terms of time? Anyone? No, right? We don't have in terms of time. We only have the space only. So do you think the partial derivative of u over t should be cancelled? Anyone?
Yes.
Yes. So there is no velocity with respect to time. If you try to differentiate in terms of time, this is equal to 0. So we can cancel out this term. Okay, this is equal to 0. So what we have now, right? Actually, we have this term u du over dx plus v du over dy. So what next? What we need to do, everyone? What we need to do?
Substitute.
Yes, perfect. So substitute u. This is u, which is x squared minus y squared plus x, and du over dx. What we need to do? How to get du over dx?
Differentiate u with respect to x for the term.
Yes, du over dx. What do you get? 2x. 2x. Can you help me?
2x
2x only?
only. Yeah, others
Are
are
you,
0.
are you
2x
sure?
plus 1. 2x plus
2x plus 1. Alright, because this is having power of 1. You move to the other side, it become 1. 1 minus 1, 0. Okay? So, replace here du over dx, which is 2x plus 1 plus v. This is V. Negative 2xy minus y. And du over dy. What's the value?
Minus 2x minus 1.
Du over dy. So, minus 2y.
Minus 2x minus 1.
Minus 2x. Okay, when we do the derivation in terms of y, this is constant. The x is constant, this is 0. Only this one only. So 2 move front, so negative 2y. 2 minus 1 is y. The x is constant, so we have only this term. So just substitute this term. Okay. And then, next what we need to do? What we need to do? We have the coordinate here. We need to substitute the coordinate. Okay, substitute the coordinate x and y, which is 1 and 2. So
Doctor,
yep.
du over dy isn't going to be minus 2x minus 1, because when we differentiate the minus 2x, dy will go away, and then the y will differentiate it, we have 1. How is it minus 2y?
Which one? This one?
Yeah, the du over dy. How did we get minus 2y?
Okay, this is u. Okay, when we do the differentiation, du over dy, that means we refer to y only. The y will be the variable, the rest will be the constant. So when we differentiate constant, what we get?
0.
0. Okay, and then when we, okay, this is the friend, this is y, and this is y. Then we can do the differentiation of y. Okay, we can see this is the power of 2. Move front, become negative 2y. So now become 2, right? Minus 1. And then we continue plus x. So x is the constant, refer to y. So it becomes 0. And we see it become negative 2y. Okay.
Okay, clear. Yeah, clear.
Okay, now try to substitute. Okay, x refer to the power of 1. So 1. Okay, try to substitute 1 squared minus 2 squared plus 1. So this one, 2, there will be 1 plus 1. Okay. Okay, and then plus negative 2 multiply with 1 multiply with 2. Okay, negative 2 multiply with 2. Alright, so finally we will get here equal to 18. Simply equal to 18. Okay, so far you guys understand? Okay. So now we proceed on the y direction. Ay equal to, remember that the ay is the partial derivative of b. This is from the derived formula that we discovered before this. Okay, this is u. We change only this one. dv over dx plus v dv over dy plus w dv over dz. Okay, we know that this is cancelled and this is cancelled. So we need to find the equation for this. Okay, u. This is u, right? Just substitute here. Okay, x squared minus y squared plus x. And this is dv over x. This term. So try to differentiate in terms of x. Okay. So what do you get when you try to differentiate in terms of x?
Minus 2y.
Minus 2.
Okay. In terms of x is minus 2y, and then okay, only this, right? Okay, and then v plus v. This is v. Negative 2xy minus y. And dv over y. D differentiate in terms of y. So what we got here? Negative 2x minus y. Okay. So substitute back the equation. Okay, substitute coordinate 1 and 2. Okay, this is 1 squared minus 2 squared plus 1. Negative 2 multiplied with 2. Okay. And then plus negative 2 multiplied with 1 multiplied with 2 minus 2. Negative 2 multiplied with y minus y. Okay. So finally we will get 26. Okay. So far this is clear, yeah, for you. And then the next question, the velocity component in the direction of 40 degree. This is having the angle. Okay, how to express in terms of 40 degree? Okay, first we need to draw the coordinate system. This is our coordinate system. This is x, this is y. Okay, we want to have the vector in terms of 40 degree. Okay, 40 degree vector. So what we need to do, we need to find the unit vector n only. Okay, we name as the n. So this is the question B. So n, the unit vector means the magnitude is 1. Okay, so this is x. So we can do the cos 40. This in terms of I, and plus sine, because we need to find the y direction, 40 in terms of j. Okay, so after we get the velocity, okay, where is the velocity? You can see the velocity component. So first, after we get this, the unit vector n, we need to find the velocity. Why we need to find the velocity? We will apply the dot product. Okay, so we need to find the velocity. Okay, it is given already in the question, right? So what's the velocity? It is given. The velocity is given, which is x squared. We can substitute with the coordinate 1 and 2, which is 1 squared minus 2 squared plus 1. This is in terms of I direction. Minus 2 multiplied with 1 multiplied with 2 plus 2 in terms of j direction. So from here, after we substitute the value, we can get the vector form of velocity. Okay, so here we can simply say that it is negative 2i, okay, minus 6j. Alright, remember that this is when the n product dot with the velocity vector, we will get the parallel vector. Okay, so we can apply the velocity dot product with the unit vector n, because we need to know the magnitude multiply with the direction. This is the dot. When this is parallel, when this is v, okay, and this is n, we need to apply dot product v dot n in order to get the parallel section. Okay, when the v cross product with the n, we will get 0. Okay, we cannot use this. This is for parallel. Okay, I hope you understand. This is actually the basic concept of calculus or any kind of mathematics previously that you learned. Okay, so velocity, just put here the velocity, negative 2i minus 6j dot product with the cos 40i plus sine 40j. Remember that when we use the dot product, the dot should be I with I, j with j. Alright, the I dot with I, you will get 1. The I dot with j, you will get 0. So that means negative 2 cos 40. Okay, negative 2 cos 40i. Okay, I multiply with I is equal to 1. It already cancelled. Okay, and then I multiply with j is 0. So negative 6. Negative 6 multiply with sine 40. So j multiply with j is 1. So what we got here is actually negative 5.39. That is the vector form in the 40 direction. So you can see it is negative, means it is counter from this direction. Okay. And finally, the direction of maximum acceleration. So we do this one last. The direction of maximum acceleration. Okay. We know that this is B, sorry, this is C. Okay, in order to get the direction of maximum acceleration, we need to know the acceleration first. Okay, so where's the maximum acceleration? Is it AX or AY? Anyone? AX, what we got?
Is it AY?
Okay, AX is this value. AY, which value?
26.
26.
So which one we should consider as the maximum acceleration, AX or AY?
AY.
EX.
Huh?
EY.
Okay, we definitely consider the AY. Okay, because the value is maximum. So A max is actually AY. So AY, we know already. Okay, where is the AY? Okay. Okay, first, okay, we already know. However, we cannot simply put A. Okay, we know already AY is 26, but AX is 80. When we consider it is maximum, it is the combination of both. Alright, A maximum is actually, okay, AX in I direction, okay, plus AY in J direction. So AX is 18I plus AY is, okay, 26J. Okay, so from here, this is the coordinate system. This is Okay, this is AX. AX is 18. And okay, sorry, this is AY. Okay, so the total is here. Okay, this is the total acceleration, A max. So the question asks to find the angle here. So AX is, okay, AX here is 18 and AY here is 26. So how to get the theta here, anyone? How to get the theta? Is it the
Tan
tangent?
inverse. Tan inverse.
Tan
Tan inverse
Tangent
26
theta
over 18.
equal to TOA. Okay, 26 over 18. So finally we will get the theta equal to
55.0.
55.3. Okay, I think that's all for today's session. Okay, and then tomorrow we're going to continue. Okay, do you have any questions so far?
Doctor,
Okay,
I have regarding the quiz.
okay,
I tested last night about the mathematical questions. They used full volume, not displaced volume. So is it? I think the I don't know what happened, but